indoctrinating folks. Reminding you, even though the fair is also experimental math seminar, and with one exception, that Nathan's father is allowed to take pictures, otherwise there are no electronic devices. Thank you.
All right, thank you to my advisor, Dr. Z, for the introduction, and to the rest of my committee and everyone else who's here. So as you can see from up there, I'll be talking about nested recurrences using experimental mathematics. So here's the plan for the talk. We're going to talk about what are nested recurrences. If you've been to talks of mine before, you probably know what nested recurrences are, and you've seen a lot of the stuff from that part of the talk. But then we'll talk about sort of the two main contributions I've made to the area. One is about discovering more solutions of this type, which we'll talk about in this part, so this term will make sense when we get there. And then we'll talk about some new weird stuff. That's the best way to describe it at this point. So to start, we're going to talk about I'm going to assume most of you are familiar with this stuff, but just a recurrence relation, in case you haven't seen this before. It's just a way of describing values of a sequence in terms of previous values of the sequence. So in this talk, everything's going to be integer sequences, and whenever you have a recurrence, well, here's an example of a recurrence. We're going to use capital letters to denote recurrences. So this is the famous Fibonacci recurrence. That's a pretty simple recurrence. So we're going to call something a solution to a recurrence if it eventually satisfies the recurrence relation. The terms do that. But not every term can satisfy the recurrence because, well, if you look at this, the first term can't satisfy this because there's no zeroth term. So you have to have some sort of initial condition. And so you need at least two initial conditions for the Fibonacci recurrence, but we're allowed to have more initial conditions than we need. That's going to be important. So linear recurrences are the simplest type of recurrence. So this is where you have your term defined by a linear combination of previous terms, like the Fibonacci numbers. So that's a linear recurrence, and here's the first few Fibonacci numbers, which is, again, if you're not familiar, just to get this term, you add the previous two terms. So the term linear recurrent is going to come up a lot in this talk. That just means the sequence eventually satisfies a linear recurrence. The first bunch of terms may not, but the terms eventually will. So these are really well understood. There's a nice way of finding closed forms for solutions of these, and there's an important theorem in combinatoric/recurrence theory that a sequence is linear recurrent if and only it has a rational ordinary generating function. So more complicated, you can have, and of course, nonlinear recurrences. This is nonlinear because we're multiplying two of the terms together. So these come up a lot, and there's no general way of solving these, and they're often highly sensitive to initial conditions. Like if you've heard of chaos theory, that just means small changes to the initial conditions cause wide differences in the eventual behavior. So we're going to focus on a specific class of nonlinear recurrence, nested recurrences. So this is a nested recurrence because there's an A inside of an A. So Douglas Hofstadter is one of the early people to look at these. And these are, the theme is going to be that these are extremely sensitive to initial conditions. And there's going to be a wide variety of behaviors for solutions to nested recurrences, even to just one recurrence. So just changing the initial conditions will cause all sorts of craziness to happen. And these are so poorly understood that there are many open questions of the form: does this sequence actually exist? So just to whet your appetite a little bit, here are plots of four sequences. So here you can see one that looks kind of linear with some noise. Here's one that there's a weird-looking, fast-growing thing and some smaller things down here. This one kind of looks like a staircase with a few other random things on it. And this one sort of looks like a waterfall of some sort. So it turns out these things all satisfy nested recurrences. In fact, they all satisfy the same nested recurrence. So which recurrence is that? Well, it's the Hofstadter Q-recurrence. Well, this slide's on the Hofstadter Q-sequence, which is actually the first sequence on that slide. So this was famously put in on page 137 of Douglas Hofstadter's classic Gödel Bach. And that was published in the 70s, but Hofstadter looked at the sequence in the 60s. And the recurrence is Q of n is Q of n minus Q of n minus 1 plus Q of n minus Q of n minus 2. And like the Fibonacci sequence, he gave it the initial conditions 1, 1. So for the rest of the talk, we're going to just use angle brackets to denote an initial condition. So if you see like a vector of numbers, that just means these are first term through however many terms there are in the list. So this should remind you a little bit of the Fibonacci definition, and for that reason this is known as a meta-Fibonacci sequence. So in the Fibonacci's, it was to get the nth term, you add the n minus first and n minus second terms to each other. In this one, to get the nth term, you look at the n minus first and n minus second terms, but then those tell you how far back to find terms to add together. So let's just do an example of calculating q of 3. So q of 3 is q of 3 minus q of 2 plus q of 3 minus q of 1. And you replace the inner expressions with the values. In this case, they're just from the initial condition. And then you just rewrite things, and q of 3 equals 2. And you can generate more terms. If you want to do this by hand, power to you. But computers can do this quickly. So these are the first few terms. So it starts out kind of nice. The terms are growing slowly, and then there's a little bit of jump. Then it's no longer monotone, and then who knows what happens. So here's that plot from the first slide. This is the first 10,000 terms of the sequence. As you can see, it's approximately linear. This line is y equals x over 2. So slope 1/2. But there's this noise that seems to come up in sort of a periodic pattern. So what's actually known about this sequence? Not much. So the pattern of the plot seems to continue, but no one can prove it. We know that if the limit of qn over n exists, it must be 1/2, but there's no reason a priori for this limit to exist. So in fact, we'll see lots of other solutions. It's actually true that any solution to the Q recurrence, if that limit exists, it must equal 1/2. And I think for every single solution we're going to see in this talk to that recurrence, the limit is not going to exist. So there's no reason it needs to exist. And we know that this sequence is well defined for the first 10 to the 10 terms. So what could make it stop? Well, what would happen if q of n minus 1 is bigger than or equal to n? Then you try to calculate q of n, and this index would be less than or equal to 0. But the first term was q of 1. So what does that mean? Well, that means we can't define q of n in that case, and we say that the sequence dies at index n. So the big open question is, does the Q sequence die or does it live forever? We think it lives forever, but no one's been able to prove that. And I didn't do that either. I proved other things. So we're going to cheat a little bit and define the values of these sequences at non-constant indices. We're going to define them to be 0. And we want to do this because it's going to allow us to consider a wider variety of solutions. So we have two notions of death now. We're going to say that a sequence weakly dies if it dies in the previous sense. But a sequence can still be finite, even with that convention. And that would happen if, let's say, you keep computing terms, and then q of n minus 1 becomes, let's say, 0. Then you try to compute q of n, it depends on itself. That's not fixable, not even by something like this. So those sequences, those die no matter what you try to do. So we use the term strongly dying for that. So these are my terms. You won't find this elsewhere. So yeah, this is going to allow us to consider solutions that grow faster than n. And you could still phrase the old question about the Q sequence. So it's not really cheating. It's just a different convention. So we're going to be looking at solutions in general. What can we say about other nested recurrence sequences? So a lot of the sequences we'll look at will be the same recurrence, but with different initial conditions. But also some of them will be with other recurrences that are similar. So now there's two sort of regimes of solutions to nested recurrences. The first, which I'm going to just talk a little bit about, are slow solutions. So an integer sequence is called slow if it's monotone increasing and by 0 or 1 at a time. So it's monotone increasing and it hits every node. Also, it starts at 1. So there are solutions to nested recurrences like this. So here's a slow sequence, and the number of times each integer appears other than 1 is 1 more than the biggest power of 2 that divides it. So like 2 appears twice, 4 appears 3 times, 8 appears 4 times. So this sequence satisfies this recurrence, which should look very similar to the Q recurrence, the only difference being this -1 here. And then same initial conditions. This is just a very slight perturbation of the Q sequence gives you this very nicely behaved sequence. And I mentioned this thing about the 1 appearing twice and how that should disturb you a little bit. If you use 1, 2 as the initial condition, that just cuts off this 1 and we're really happy. So Steve Tanney at the University of Toronto and various co-authors have studied these sorts of things extensively. And a lot of times you can actually get combinatorial interpretations for these in terms of trees. So if you were at my GCS talk a couple weeks ago, I talked a little bit about that stuff. But there are other ones of these that don't have such interpretations that we know about. So here's a few other slow sequences that are known. So this is the Hofstadter $10,000 sequence, defined by another nested recurrence. The different sort of term we have is this one. Same initial condition that we keep having. And those are the first few terms. And famously what happened was, so Hofstadter was the first one to look at this. Conway was able to prove that the limit of an over n is a half. But he had no idea how fast it was converging. So he thought it was hard. When Conway thinks something's hard, he puts a money prize on it. And Neil Sloan can confirm that the prize on this sequence was $10,000. But then, much to Conway's chagrin, 3 years later, Colin Mallows actually figured it out. At which point Conway tried to claim, I only offered $1,000. Neil was there.
It didn't take him more than a couple of months.
Oh. Yeah, and then another notable slow sequence is the Hofstadter V-Sequence. So this doesn't have any terms like this. It also doesn't have any of those -1s or things like that. The only difference with the Q recurrence is this 4 instead of a 2. And then we need a length 4 initial condition in order to start doing anything. But if you do 1, 1, 1, 1, you get this sequence where every number greater than 1 appears at most 3 times. And then here's a result of mine. And this is the last I'm going to say about slow sequences. So if you take this third term that just generalizes the Q recurrence in a natural way, and you use 1, 2, 3, 4, 5 as the initial condition, you get this sequence, and every number appears at most twice in this sequence. All right, was that a question? Yeah.
In general, in that last sequence, you have every multiple of 3 repeating twice except for 3 itself?
Yes, but there are other numbers that appear twice also. It's like 17 appears twice. But I can describe exactly which ones they are. So the rest of this talk is going to be more related to these sorts of things. So when I use a Q with some sort of decoration on it, that means another sequence that satisfies the Q recurrence that isn't the Q sequence. So here I'm using Q sub G, because it's going to be the same recurrence, but a different initial condition. So this was something that Golem looked at. So instead of 1, 1, the initial condition is now 3, 2, 1. And here's the sequence. And hopefully you should see a pattern, and the pattern's going to keep going. So there's a bunch of 3s, and then all the other terms go up by 3 every 3. So you can write that like this. And so I'm going to actually guide you through the proof of this. It's not very difficult, but this proof is sort of the basis for most of the stuff I've done, sort of generalizing this proof and automating this proof. So it's a proof by induction, and there are 3 cases here, so there's going to be 3 parts to the induction. So usually with inductive proofs, we do the base case first, followed by the inductive step. We're going to do the inductive step first. So I'm just going to do one of these. So for the Q of 3k, first you just plug in the value into the recurrence, and then you expand things out, and then you apply the inductive hypothesis to those inner guys, and then you just keep rewriting, and then we get to use the inductive hypothesis again on this term. And then we simplify, and we get 3k minus 2. So assuming that the 3 times we apply the inductive hypothesis, assuming we were okay doing that, Q of 3k is 1. And then the other 2 cases are similar to this. And we also need a base case, but it turns out that the base case is exactly those 3 values. So if those 3 values work, everything else goes through. So just another notable solution in the same vein is due to Ruski, same recurrence, and now the initial condition is 365, 368. Golem's solution didn't require that strong death convention, but Ruski's solution does, because otherwise it would die immediately, because 8 is bigger than 7. But with that convention, you get this pattern. So there's a bunch of 3s and a bunch of 6s, and hopefully you recognize those other terms. They're all Fibonacci numbers, but they start at 5, but that's okay. So you can write it down like this, and you could try to prove it, and the proof would look basically identical to the golem proof. It would just have a different formula that you're trying to prove. And the base case would be different. All right, so the next chunk of stuff is we've seen the golem solution, we've seen the rasmiy solution. Hopefully you're thinking, are there more solutions like this? The answer is yes. So let's talk about how we might find these. So our goal is to find a bunch of solutions like that. And the key property that we're going to clue in on is we want them to be interleavings of nice sequences. What is a nice sequence? I'm not going to define that rigorously, but constants are nice, linear things are nice, polynomials are going to be nice, the Fibonacci numbers are nice. Yes?
So the interleavings, do they have to be, do they have to follow some pattern, or is it maybe random interleavings? I'm imagining they just have to be kind of nested together, right?
Yes, we'll actually see some things that you might call interleavings with randomness later,
Okay.
but those don't come up out of this. Those come up sort of consequentially. I wasn't expecting to see those, and then they happened. But that's in the third part of the talk. So the way we're going to do this, though, is we're going to try to generalize the proof of golem solution that we saw, but we're going to try to do that without actually knowing what any of the assumptions we're making are. And we're sort of just going to make the assumptions as we go, and then at the end check to make sure all the assumptions we made are consistent. And if they are, hooray, we found a solution. So that sounds, the golem proof is very tedious and mechanical, especially if you want to make a bigger version of it. So when things are tedious and mechanical, we feed them to computers. And because computers are very good explorers for this sort of thing. So the same method's also going to work for other recurrences. And it's going to rely heavily on symbolic computations. So this slide is going to make almost no sense whatsoever, but I'm still going to go through it. But then the rest of this part of the talk is explaining what this slide is. So this slide goes through the steps for how we actually run an algorithm to find these solutions. So first we need to figure out how many sequences are we going to interleave together. For golem and rasmiy, that was always 3. But in general, it need not be 3. It could be more, it could even be 2, or even 1. Then we need to decide what are our subsequences going to look like. And the 3 options that we're going to consider here are they could be constant, they could be linear with slope 1, or they could be faster growing than that, meaning linear with slope greater than 1, or like quadratic or something that goes faster than linear. We're not considering things that have slope between 0 and 1. Those don't seem common, but they do come up occasionally. But it's easier to just ignore those. So then step 3 is we basically try to do the inductive step of the golem proof in terms of these unknown mu sub r's, but we don't know anything about the mu sub r's. So at that point we end up having to make some assumptions about them. And then once we've done that, we have to check to make sure everything we've done was consistent, which is going to result in some constraints on some unknowns, which are going to be these mu sub r's, and we're actually going to end up throwing in more unknowns along the way. And then we try to satisfy the constraints just to make sure these assumptions are consistent. And then we need a base case, so that's going to be the same as finding an initial condition to make everything go through. So I made sure to engineer an example that shows most of this stuff in action. So we've seen 2 period 3 solutions to the Q recurrence. We're going to find another one. It's not going to be golem's sequence, and it's not going to be rasmiy's sequence.
It's going to be the fox.
It's going to be one of many Fox sequences. if you look for Nathan Fox Hofstadter in OEIS, there's like 6 pages of them or something. This is one of them, though. So the sequences that we're going to look for one that's linear with slope 1, one that's constant, and another one that's constant. So maybe it wasn't the best notation, but we're using it anyway. So it's going to be linear, constant, constant, whereas golem was linear, linear, constant. So now we try to unpack the recurrence. So this is like the inductive step of the golem argument. So we just write things out, and then we get to expressions like this that right now we can't go any further. And then we do that for the other 2 cases. So we get these expressions that are right now they're terminal expressions. So what do we do with those? So we have expressions with k's in them. We also have expressions without k's in them. Well, if it doesn't have a k in it, that's just a reference to a specific index. That's a constant. So we just add that as another unknown and just keep going. What if it does have a k? Well then, in order to do the induction properly, we need to know what the congruence class of this mod, well 3 in this example, a general mod m would be. Because that will tell us which case of the formula to apply in the inductive step. So in this particular case, we end up needing to look at the congruence classes of mu1 and mu2. Mu0 doesn't matter. So the computer doesn't know what we're looking for, so the computer just tries all possible congruence classes and then says what it finds. But we know what we're looking for, at least I know what we're looking for. So we're going to assume that these are the congruence classes. So mu1 is going to be divisible by 3, and mu2 is going to be 2 mod 3. So great, now we can unpack these further. So this guy's 2 mod 3, which means we land in this case, so we can just replace this with mu1. And then this guy we land back in the first case, so we have to replace it with this expression, and then we simplify. And we do similar things for the other 2 expressions. So great, so that's where we are now. All of these expressions are in terms of constants except for this k here. So now we have to check to make sure things are consistent. So we need to make sure we have the correct type of sequence come out of that unpacking. So it turns out that first expression we got is linear with slope 1, which is what we wanted. And these other 2 are constant, which is also what we wanted. So it passes this naive check. So now it's time to set up some constraints. So there's a lot of unknowns floating around. There's 5 unknowns. There's mu0, mu1, mu2, and then these 2 things. So in general, we need constraints to make sure the guys on the left equal the guys on the right. So in this case, we get a tautology, but that's okay. We oftentimes get tautologies, and we can just work with them. They're always true, so they're satisfiable. This one's not a tautology. This one's actually interesting. And here's another interesting one. And then we also need to actually enforce our congruences. That's more constraints. And we also need to have constraints that enforce our strong death condition. So if it turns out that this index is not positive, we need to assume this term has to be 0. So this is a constraint that's of the form if something, then something. And we also sometimes need a few other technical constraints. There isn't much else that comes up in this example, but there are occasionally other things we need. So once we have our constraints, we try to satisfy them. So usually we have more degrees of freedom than we have constraints. So usually if there's solutions, there's actually an entire family of solutions. So what I have up here and what this example is not just one solution to the Q recurrence. It's actually an infinite family of solutions to the Q recurrence. So we have these constraint systems, and Maple knows how to solve these. And one solution that we get here is these are the new values, and this is Q of 1, because now we actually know what those indices are, and this is Q of 2. So this sequence is a little different from the ones we've seen before, in that there's a couple rogue terms at the beginning that don't satisfy the recurrence, or that don't satisfy the pattern we end up with. But that's fine. It just eventually satisfies the pattern we want. So then all that's left is to find the initial condition. So what we have to do is we have to look carefully at our induction and see what we assumed. And then so that gives us, well, which k values were safe, which ones weren't. The ones that weren't, we have to check those separately. And then that gives us an initial condition. So in this case, we realize that just k equals 0 and k equals 1 were unsafe. So that corresponds to indices 1 through 5. So that means we have to use, well, 1 and 0 were forced by our extra constraints. And then 3, 3, 2 is just extrapolating the pattern. So 1, 0, 3, 3, 2 is the initial condition we get, and 1, 0, 3, 3, 2 generates this sequence, where there's 3s and 2s, and then multiples of 3. So that's different from the Golomb sequence, different from the rasmiy sequence, but another period 3 solution, though it has these 2 terms at the beginning, but whatever. So now just a couple final slides in this part to sort of summarize some of our findings with this. So these things are very common. We'll see about how common they are soon. But there also are some sort of symmetries among the solution families. There's one very obvious symmetry that I'm going to mention in a couple slides and sort of mod out by when enumerating stuff. But there are other symmetries that are sort of appear to be lurking beneath the surface and are sort of hard to identify. But a couple other things we found is that you can actually interleave any linear recurrent subsequence as long as all the coefficients in a homogeneous linear recurrence that it satisfies are positive coefficients, and that the sequence grows exponentially. So it doesn't just have like an equals an minus 1 as its recurrence. And you can also put polynomials of arbitrary degree in there. We've seen constants, which are degree 0, and then linear, which is degree 1. You can actually also get quadratic and cubic and quartic subsequences coming out of this. And for the Q recurrence, if you're interleaving 3 times d sequences, you can get a degree d polynomial. So here's a plot of one with 9 interleaved subsequences. This is a logarithmic axis so that we can actually see all of the subsequences. Otherwise, that top one would just dominate the whole picture. That top one is a cubic subsequence. This middle one's a quadratic subsequence. This bottom one's linear. And then these are constants, and some of them are repeated because there's actually 9 things being interleaved here. So now let's just say, what do we know about the Q recurrence? So this is that symmetry I mentioned that's very easy to notice. So if you remember the form of the Q recurrence, it doesn't actually refer to any indices explicitly. It just tells you, it just refers to indices relative positions. So that means that if you take all the terms in your sequence and shift them over, it still satisfies the Q recurrence. So that means that we're going to sort of have 2 ways of looking at how many solutions we are, because now we're about to use our algorithm to count the number of solutions. So m equals 1, there's nothing. M equals 2, there's 2 interleaved there are 2 infinite families of solutions, but if you mod out by this shifting relation, there's actually only 1 type of solution. So for m equals 3, where we've already seen 3 solutions, there's 1 more that we haven't seen, which looks a lot like the example sequence we had here, but it's sort of like a reverse and 3 minus of that sequence in a sense. So that's where I said there's some more interesting symmetries that I haven't really examined too much. So 4 has 5 families, 5 has 7 families, 6 has 86 families. There's a lot more going on there. And yes, these 86 do include these 4 and this 1, but the family here that includes this also includes a lot of other things that don't have period too. So this is strictly more general than that. 7 is actually a little bit easier than 6, so there's less going on, probably because 7 is prime. But then 8, there's a lot more. And I say at least here because some of these Maple was throwing out warnings about possibly losing things. So it found this many, but it may have lost a few.
Is 12, 35, 294 in OIS?
That's not in OIS because I don't, 2 reasons. Number 1, I don't quite know how to describe it succinctly enough. And number 2, I can't quite prove that it's correct. It's pretty much correct, but there might be some other sorts of solutions with other sorts of things going on that I didn't think about. And then 9 has a lot more solutions. That's where you start getting cubic things. All right, so that's the end of that part. So before we move on to the next part, are there any questions right now? Okay. So what we've done so far is, here's the behavior we want the sequence to have. What initial condition is going to do that? So now we're going to use some sort of a different scheme. So now it's going to be, here's the type of initial condition we want. What sort of behavior do you get? So when we give so we're going to talk about various special types of initial conditions. But we want to consider infinitely many of these simultaneously. So our initial conditions are going to have symbols in them. So in this context, we can talk about weak death or we can talk about strong death. So here's the general method we're going to use. Again, this slide may not make a lot of sense without examples, but the rest of this part of the talk is examples. So we start with some sort of symbolic initial condition. So right, you should think like maybe 1, 2, 3 up to n, for some n. Hi, Jake. So then you just generate a bunch of terms. And by generate a bunch of terms, I mean in terms of symbols. So if like n is a symbol that appears in your initial condition, these terms are likely to have n's in